So we were talking about confined aquifers, and then we were talking about the gravity or ordinary well. So to explain the difference between the gravity wells and the artesian well, I'll draw a small diagram here. So we have this water saturated medium that we call as aquifer, and on top we have this ground surface. So just let me color that up for you. Okay, before that, so this is the borehole that I'm making inside the ground, or this is the well. So now you see the water table in inside the ground and water table inside the well. If they are same, then it is called as a gravity well or an ordinary well. Okay, if the water table inside the aquifer as well as inside the well they are same, then we call that as a gravity aquifer. So this whole area, this all is sandy soil. Okay, let me redo that from the start. So let's say that we redo that. This is the ground surface, and this hole is sandy soil that is filled with water, that is called as unconfined aquifer. And let's say this is all rock or clay soil, and the water table inside it, sorry, and the water table inside it, this is here, this is water table. So that means all the soil below the water table, this is all saturated. So this is the initial condition, and once I make a borehole or a well inside the ground, that means I'm making a well. This is the well that I'm making. So this is the well. So once I make the well, what will happen? The water table inside it, this will remain the same. So you see here, in such a situation, when the water table inside the soil and inside the well they are same, then it is called as a gravity well. And on the contrary, if we have a confined aquifer, and this is called as an gravity aquifer or simply an aquifer. On the contrary, if we have a situation, redraw that. If we have a situation here, let me check if this recording is happening. Yep, it is happening. So if we have, this is the ground surface, and this here, this all is the sandy soil that is filled with water. Okay, but on top of it and below it we have impermeable soil, that is clay soil or maybe rock. So this is all impermeable. The brown color represents the impermeable soil that does not allow water to flow through it, and blue color indicates the permeable soil, that is an aquifer that allows water to flow through it. So what we're going to do is that we are going to make a well up to the bottom of the aquifer. So in such a situation, what will happen? The borehole, in the borehole, the water table will be at a higher elevation than the actual water in the ground. So you see here, the water table inside the well is at a higher elevation than the water inside the aquifer layer. This is called as an artesian well or a pressure well. So it says that a well that is tipping water from an aquifer confined between two impermeable layers, and water is under pressure greater than the atmospheric pressure. So that's why we have a higher water table as compared to its surrounding. Aquiclude is a soil deposit which is impervious. So this is an aquiclude, and this is an aquiclude that do not allow water to flow through it. So these are the definitions related to the pumping out test. So we go back to pumping out test now. So in pumping out test, we have the first situation here, that is an unconfined aquifer. That means if I draw it simply, so that means this is the ground surface, this is the impermeable layer of the aquifer. So this all is water bearing stratum or an aquifer. So now this is directly on the ground surface, so that's why it's called as unconfined aquifer. So this situation is mentioned here in the diagram. So to draw it in simpler diagram, so we'll make a borehole here. This is the main borehole, okay, and then we have two observatory wells. This is smaller and this is smaller on the sides, okay. So once we are doing it, so what we are going to happen is that we are going to pump water out of it, okay. While we are pumping water out of it, what will happen? The water table will start to drop down in the well. So we are pumping, and a time will come then when this state is situation that the pumping rate is equal to the inflow rate. That means while we are pumping water, there is no more fall in the water table inside the well. So that is called as steady state condition, okay. So water is pumped out at a constant rate, and we keep doing it until we have reached a steady state condition. And what is a steady state condition? In a steady state condition, the rate of outflow, that is discharge, that is being pumped out, is equal to the inflow water from the surroundings. And how it is confirmed? This water table does not fall down. Initially water table was here and it has fallen down up to this point due to pumping, but it does not fall below. So that means we have reached a steady state condition. So once the steady state condition is observed, then we do the measurements. So this portion, this hole is called as a test well, and this small well, this one and this one, these are called as observation wells. So we will see that what is the height of water table here in the well, and what is the height of water table in the first observation well, what is the height of water table in the second observation wells. So if we draw the center line of the observation wells, so the radius of the well, okay, it may be indicated as not the radius, the distance of the first observation well from the center of the test well is r2, and of the this one second observation well is r1, and the height of water table is indicated as h1 and h2 in the observation wells from the bottom, that is the impermeable layer or the aquiclude, okay. I will try to redraw these things so it's more easier to understand. So once we have reached the steady state condition, that we do not see any drop in the height of the well, so of the water in the well. So this is the second observation well, this is the first observation well. It is having a distance r2 from the center, and this is having a distance of r1 from the center of the test well, okay. And then we note the height of water table in the second well, that is h2 from the this bottom impermeable layer, and this is height of water table in the first well, that is h1. So these are the values, and this is the formula here. This is the formula that we will use. So permeability of the soil, this whole soil in which the flow is happening, is equal to 2.302 Q. This is the discharge that is coming out of the well. This is the discharge, and R1 and R2. R1 is the distance of the outer observation well from the center of the test well, and R2 is the distance of the second observation well from the center of the test well, and H1 and H2 are the respective heads in case of the first well and the second well. So please remember, this one is the first well, this is the second well. So please remember that we have to do calculations from the bottom of the aquifer, that is the impermeable layer, okay. A lot of students do mistakes while doing numericals, but we'll do some sample numericals to clarify things further. The second case is a confined aquifer. So you see here, this is the actually aquifer that is confined. The above layer, this one, these are all aquicludes, and that means they have very low permeability. Water is flowing in this aquifer only here, okay. So this is a confined aquifer. Why is it a confined aquifer? Because it is pressed between impermeable layers, okay. So we have dug up the well up to the bottom of the confined aquifer. The H is the height of the aquifer, that how much thick is the aquifer, and then again this is the test well. Q discharge is coming out, and we wait for the steady state condition, and then this is the first observation well and second observation well. And you see here the difference now here is that the height is now calculated from, this is H1 and this is H2. Now the height is in comparison to the water table inside the test well. So we are comparing the height not from the top of the aquifer, not from here, but from the top of the water in the test well. So please remember the differences. H1 and H2 is here, and these values are same, R1 and R2, that the distance of the first well from the center of the well, test well, to the distance of the second observation well to the center of the test well. And the formula here that we have is equal to Q into log R1 over R2, 2.727 H1 minus H2. Q is the discharge water that is coming out through the pump. R1 and R2 are the distances from the center of the test well. H1, H2 are the heights as indicated in the figure from the test well water table, okay, and H is the thickness of the confined aquifer. So we will do some sample numericals to further clarify things. If you still have an ambiguity, I'm sure that will be answered while we are doing numericals. So after pumping out test, we have pumping in test. So it is used to find out permeability for individual stratums. It is economical than pumping out test, but it is less reliable and give value close to the hole. The first one is open-ended test, in which water flows out to the bottom. So what happens is this is the layer, and this is the ground surface. So what in an open-end test, what we'll do, we will insert a tube. That's a hollow tube, okay, and we will fill it with water, okay. So we will fill this with water. When water table is filled up to a point, let's say up to this point, so what we will do, we will turn on the stopwatch, and after a certain time we will see that how much is the drop in the water table in this hollow tube that you inserted inside the ground. That because that is flowing out inside the soil stratum, for which we are finding the permeability, okay. So it will tell us the permeability of this particular soil layer, only this strata in which we have inserted the tube. So this is the open end, and what we are doing is that it is simply, you are draining water and you see the time it takes to drop the height in the inside the tube, and from the drop and the time taken, we can find out the permeability of this particular strata. The second test is a Packer test. Water flows out, flows out from the sides of the section of a hole enclosed between packers. So in a Packer test, what we do, the process is same. This is the ground surface, this is the layer for which you are interested to find out the permeability. You will insert a tube, but here we have packers. Packers are just like, you see, corks. So inside the cork, and we have slits here, so water will only flow out from the slits. If I zoom this up, so this is how it looks like. This is packer here, this is packer here, and we have slits inside the pipe, and water flows out from here, but water does not, so water flows only in this section. So this is the packer test. It works similarly, but in open-end test we have hollow end at the bottom of the tube, but in packer test we have slits on the side of a pipe and cork on the top and cork on the bottom, which we call as packers, and water flows out from the side. So we will then again measure the amount of water in a particular time that is flowing out. That is the pumping in test. So now coming to the numericals related to the pump out test. So this is a figure here, okay, and I'll try to solve the numerical alongside the question. So the question says that we have unconfined flow, that means it's an unconfined aquifer. After attaining the steady state, following conditions are used. Discharge is 20 meter cube per hour. Calculate the Q. So that means small q is 20 meter cube per hour, okay. And to solve this, I need to know the formula for the permeability of an unconfined aquifer. I'll go back to the numerical, and it says it is equal to 2.303. Let me write the formula here. 2.303 Q log of R2 over R1 over pi H1 square minus H2 square. So now we'll find out the values. So important thing is calculating the values of H1 and H2, because this is little tricky. If we go back to the diagram, so H1 and H2 are the values from the bottom of the impermeable layer. Okay, so we will go back and go to the numerical here. Now you see here R1 is simple. This is R1, that is 61 meter, and this is R2. So we have the value of R1 and R2. Now I need to know the H2 and H1. So this is H1. This is supposed to be H1. This is H1 and this is H2. So we have to do the calculations ourselves. So the total depth is 12 meters. Okay, let me use a thinner pen. This is 12 meters and it says groundwater table is 12.4. So this is 2.4. So the remaining height is, let's see, the remaining height is, so I'll subtract 12 from 2.4. It gives me 12 minus 2.4 is equal to 9.6. So this is 9.6 meters, the distance from water table to the bottom of the impervious layer. So I need to find H1. So you see it is 0.5. So I have to subtract 9.6 minus 0.5. So it gives me 9.1 meters. So H1 is 9.1 meters and H2, it is 2 meters below. So that is equal to 9.6. That was the distance from water table to the impermeable minus 2. So this is equal to 7.6 meters. So H2 is 7.6 meters. Now we'll plug in the values in the formula. So K is equal to 2.303. Discharge is 20 meter cube per hour. I'm writing formulas and the values units along so I don't get confused. R2 is 20 and R1 is 65. And then we have pi, and then H1 square. Now H1 is 9.1 square minus H2, that is 7.6 square. So we will find out the values and plug the values here. So I will find out, first of all, 20 divided by 65. Let me see if I have done this correctly. Okay, just a minute. Let me go back to the numerical. Sorry, it says R1 over R2 and H1 H2. Okay, I'm right. So let's find out the values. So 20 divided by 65, and then I will find out the log. The log of 20 divided by 65. Oh. There must be something wrong. R2 over R1. Okay, this was the, oh yes, this was the mistake I was doing. It is R1 over R2. Sorry, this is, please do the correction. This is R1 and this is R2. So that means this is 65 over 20. That's why I was getting a wrong answer. So okay, I'll do that again. Log of 65 divided by 20 is giving me 0.51. Multiply that with 2.303. Multiply that with 20. So above, in the above, I have value of 17.484, and it is meter cube per hour. And on the division, I will first find out 9.1 square. Okay, 9.1 square, 7 point minus 7.6 square. So this is 25.05, and then lastly 17.484 divided by 25.03. It gives me a value of 0.6985 meter cube per hour. And then obviously if this was in meter square, so meter square will cancel out. So our units are 0.6985 meter per hour. So I can convert this into meter per second, meter per minutes, whatever you want. You can multiply it with 60 to convert it further. But this is the answer of permeability for our example. Now we move to the second example. So it says this is for a confined aquifer. So this thickness of confined aquifer, this is 5 meters, this is H. So I'll write the formula first. I'll go back and look at the formula. It says Q, okay, let me write the formula. It is equal to K is equal to Q log of R1 over R2 over 2.727 capital H H1 minus H2. And once again, H1 H2 are, this is important, that H1 and H2 are the difference in the height of water table in the observation well and the water table in the test well. So we will take that in a proper manner. So I will write the values here. Now Q, the value of discharge, is it mentioned here? Let me see, example 5.6. Where is the discharge value? Load sense, unconfined pumping well, compute K. Okay, discharge is 20 meter cube per hour. So I'll put the value 20 meters cubes per hour. This is discharge. And then log of R2 and R1, sorry, R1 over R2. So that is 65 over 20. I think this is similar numerical like the previous one. And then we have 2.727, capital H is 5 meters. This is 5 meters. And then we have to find out H1 and H2. Now H1 and H2. So we have to find the value of H1 and H2. So we have to actually find out the difference in the water table. Okay. So for that we need to find out the depth of water inside the test well. Does it say anything? Original piezometer level. I'll go back to the diagram. So this should be, I'll rub this up. So H1 and H2 are difference from the, just a minute, a difference here, the observation well and water in the test well. So we'll go back. So now we don't have actually any value given here in the numerical for the water in the test well. So let's say we say that this is at a depth of 4 meters because total depth of impervious stratum is 4.6. So let us assume this is 4 meters. So now H1, it is the difference. This is H1. Sorry, this is H2 and this is H1. So H1 is equal to, it should be 4 minus 0.5 and H2 should be equal to 4 minus 2. So this is 3.5 and this is 2. So we should have 3.5 minus 2. So now we put in the values. We will plug in the values, find out, we have already find out the value of, okay, so I'll first find out log of 65 divided by 2, log of 65 divided by 20, sorry, divided by 20. This is 0.551, multiply that with 20. So this is 10.24 meter cube per hour divided with, now 5 multiply by 2 multiply by 5 multiply by 2.727. So this is 20.45. So permeability for our soil, and this is in meters. This is in meters and this one is also in meters, so it becomes meter square because this is meter and this is also in meters. So 10.24 divided by 20.45, it gives me a value of 0.5 meter per hour. So we can convert, this is the permeability, and you can obviously convert it to meter per second or centimeter per second, whatever you are comfortable with. So these are the two numericals related to unconfined and confined aquifer. If you have any questions, you can ask them in our live class sessions. Then we move to the last topic of the permeability, that is related to the permeability in different directions. So the coefficient of permeability of a disturbed sample may be different from that of undisturbed sample, even though the void ratio is same, because once the void ratio is disturbed or the arrangement of soil is disturbed, so the flow of water will be using a different path, so it will result in a different permeability. This reason may be due to change in structure or due to stratification of the undisturbed soil, or both. In nature, we may have fine-grained soils having structures either flocculated or dispersed, and two fine-grained soils at the same void ratio, one dispersed and other flocculated, will exhibit different coefficient of permeability. So this is very important. Now this is the last topic of permeability, that if we have layered soils, then how the permeability will vary if we are considering layer in horizontal direction and if we are considering layers in the vertical directions. So the last topic regarding permeability is the permeability of a layered soil system. In nature, we know that generally soil exists in different stratas, and different stratas might have different permeability. So in this regard, permeability is found out for a total system for two cases. First one is when the flow is horizontal, and the second one is when the flow is vertical. So on the left side, we have a case where the flow is horizontal. That means the flow is in direction parallel to the stratification layer, and in the second example, flow is perpendicular to the layer of stratification. Okay, so now we talk about the first case where we say is at a horizontal flow case. So in a horizontal flow case, we will imagine that flow is happening from AB section to CD, and let's say this length is L, and while water is moving from AB to CD, it is having a head loss, and let's call that head loss as H. Alright, and if Q is a total discharge that is coming inside these layers, so Q1 discharge will go in the upper layer and Q2 discharge will go in the lower layer. Upper layer has a thickness of H1 and lower layer has a thickness of H2. Upper layer has a permeability K1 and lower layer has a permeability K2, and the total thickness of the strata is HT. Now, because the flow is happening from AB section to CD, and we will have a constant head loss, that means we know that gradient is I is equal to H over L, that is the gradient. So gradient loss will be similar in the first layer and gradient loss will be similar in the second layer. So let's call that as gradient loss in I1 is in the gradient loss in the first layer, I2 is the head loss or the gradient in the second layer. And from theory, we can say that I is equal to I1 is equal to I2. That means the overall head loss of the system is equal to the individual head losses in each layer. And if we talk about the discharge, so we can say that the overall discharge of the system is Q, and it is equal to addition of discharge in layer 1 plus the discharge in layer 2. So we know that Q is equal to KIA. Okay, so plug in the values. So Q is equal to the horizontal permeability into the hydraulic gradient into the area of the flow, and in this case, what is the area? If I draw it in 2D, so this is the area. This is the area of flow. Let's call this A. So thickness is H1, and we consider unit thickness. That means whatever unit, 1 meter, 1 feet, whatever unit what you are going to use. So area is the area of cross section in which the flow is happening, and that is perpendicular to the direction of flow. So in our case, area for the first layer, if I write it here, so area A1 will be equal to H1 into 1, that is thickness of the first layer, and A2 will be equal to H2 into 1, that is thickness of the second layer. So plugging in the values for the average value, K horizontal is into I into A is equal to K1 I1 into A1 and K2 I2 into A2. Now we have already discussed that I is equal to I1 is equal to I2, so they will cancel out and we will be left with this equation, that is K horizontal into the area of cross section of the whole system is equal to K1 A1 plus K2 A2, and we have just found out that the values of area A1 and A2 are mentioned here. We plug in the values in H1 H2, and similarly for the whole system it will be the total thickness HT. So by rearranging, we will get this formula that for a system where horizontal flow is happening, that means flow is parallel to the direction of the stratification, there it will be equal to the permeability of the first layer into thickness of the first layer plus permeability of the second layer plus thickness of the second layer over the total thickness of the layer, and this will continue. Okay, for example, if we have another layer K3 H3 and so on, and let's say K and HN, and this HT will be equal to the thickness of the all the layers that are heading H1 plus H2 up to HN. Okay, so this was for the horizontal permeability. In case of vertical permeability, that means the flow is perpendicular to the stratification of the soil. Okay, so in this area, in this case, this will be the area of cross section that we need to consider. And similarly, we will consider any rough area. Maybe we can say that 1 by 1, it's your choice, because we are only concerned in thicknesses. So in this time, discharge will be constant in each layer. Q is equal to Q1, Q is equal to Q2, and this is the average discharge in the system. Permeability of the first layer is K1, so the second is K2, thickness of the layer 1 is H1, and thickness of layer 2 is H2. So head loss, while the water is traveling from the first layer, head loss is H1, while the water is traveling from the second layer, head loss is H2, and in the overall system, the head loss is H, that is equal to H1 is equal to H1 plus H2. Okay, so head loss in the, I will write it here, head loss here is H1, head loss here is H2, and overall head loss is H, and that is equal to H1 plus H2. Now as the discharge is constant throughout the layer, okay, so we'll write this equation on the separate side. When we know that the formula for the hydraulic gradient is equal to head causing flow over the length. So in our case, if we talk about the first layer, head causing flow is H1, and what is the length of the distance traveling, that is thickness of this layer, that is H1. Same, so this is I1. Similarly, I2 will be equal to H2 over H2. Okay, so we have written this equation here. And now as the discharge is same, plug in the values of K, KIA. So the total vertical permeability into I into A is equal to K1, I1 equal to K2, I2. So from derivation, we can prove that we don't need to go in the derivation, but this is the final equation in case of vertical permeability. That is, vertical permeability is equal to total thickness of the system over H1 over K1 plus H2 over K2. So you have to remember both of the equations, because a lot of numerical can come in your exam where you have to find out the permeability of the system, and you have to remember this equation. And trust me, I often mix them. So make sure that you remember that what is the permeability formula for a horizontal flow case, and what is the formula permeability for a vertical flow case. So there are 1-2 examples that are provided here in the notes that I've already provided you. So if you have any questions regarding that, we can discuss in our regular class, or maybe if you still have any questions, so we can discuss them in your ODL classes when you will come, on your psychomotor week when you come to the on-campus classes. Okay, so here is this one example here. So let me see what the example is about. I think there's no question here. So you see here they have used this for horizontal permeability. Okay, plugging in the values, and you simply have to just plug in the values of thickness of permeability of each layer, and you have your answer. So the key is only to remember the formula. All right, thank you so much for your time.